All right, so I do have a quick little warm up on here. I have board problems. I'm just going to go ahead and go through all of those kind of as a quick review, and then we will get started into today's stuff, which is graphing radical functions. And so, with graphing radical functions, we're going to talk about the idea of parent functions. And so that's kind of just that baseline function. Like we're going to talk about square root of x and cube root of x, which we've already talked about a little bit. Like I said, we should know what those ones look like. But a little bit more, get into that as a parent function. And then once we have that as a parent function, we can build upon that and then determine, okay, if we do a shift or if we do a stretch, what that actually looks like. And so we'll spend some time looking at those and then do a couple examples, turn your loose, and you can get started. So normally this would be, there's a lot of graphing that we're going to be working on. And normally I would have you be doing that on graph paper. Well, you probably don't have graph paper there at home, and we didn't have enough heads up to make sure we had graph paper available. So do it in your notebook, do it as accurate as you can, and just to get an idea of what it would look like when it's made that shift, that'll be enough. Okay. All right. So just as a quick warm up, all right, let's do the board problems first. Okay, so for this one, it says for each function, find the inverse and the domain and the range of the function and its inverse. Determine whether the inverse is a function. So this is what we've been doing from concept 5, but this is what you're going to be tested on for tomorrow. So let's start to kind of get back into this thinking of what we're working with when we're doing these. Okay, so let me see here, make sure I got. All right, so first thing, f of x is the square root of x minus 5. So again, we should know that square root of x, that parent function of it, looks something like this. And so now if I wanted to do x minus 5, that actually shifts it 5 units to the right, and then it still takes that same shape. All right, in the original function, my domain, my x values, are now from 5 inclusive all the way to infinity. And my range is from 0 all the way to infinity. So thinking vertically, I can have 0 because it does land right here on the x-axis, and then it goes up from there. Okay, so this is domain and range of the original function. Now we want to tackle that inverse function. And so if we went to that inverse function, first step, I would say, well, y is square root of x minus 5. Change it from function notation to y equals. Do the switch, so x is going to be equal to y minus 5. And now I need to solve. So in order to solve this, I would square both sides to undo that square root. And so that's going to leave me with just y minus 5 on this side. Okay. And squaring is not one that we're looking at that it's going to bring in that plus minus. When we undo a squaring using square roots, that's when it brings in plus minus. So this is just x squared. So x squared equals y minus 5. So x squared plus 5 would equal y, which is the inverse. So I'll say that's f inverse. Okay. And so once it's find the inverse, and then find the domain and range of the inverse. So domain of this inverse function, again, is just the range. So this would be 0 to infinity. And then the domain of my original becomes the range of my inverse, 5 to infinity. Determine whether the inverse is a function is based on our original. If it passes the horizontal line test, which this one would, if I were to draw a horizontal line for my blue, it's only going to intersect at one point. And so, yes, this is a function. The inverse is a function. So again, that's good review. This is concept 5 material that you're going to be tested on tomorrow. If I give you one just like this, I expect that you can find the inverse, determine if the inverse is a function, know the domain and range of the inverse, but also be able to find domain and range of the original function. All right, 39. So find each value. So this is probably the easiest one. If I wanted to compose a function with its inverse, that's that thing where it just goes in a big circle and I end up right back where I started with. So the answer to this one is simply -10. And we worked through one example in class showing why it's -10. But if you compose a function with its inverse, you just go in that big circle and you end up right back where you started with. 49. So this is taking a function composed with the inverse of another function. So this is not that circular pattern. All right, we're going to be working with f. So this function f, I don't have to touch. I don't have to do anything with that yet. But I do need to figure out what g inverse is. Okay, so if I just set this up as y equals x minus 2, do my switch. And so I'm going to say x equals y minus 2, then x plus 2 would be y inverse, which is the same as g inverse of x. So just keeping the notation straight, this is g inverse. Okay, so what they're asking us to find is what is f composed with g inverse of -3. So the first thing we have to find is g inverse of -3, which would be -3 plus 2 from our inverse function that we have down here. So g inverse of -3 is just -1. But we have to compose that with f. So now we want to know f of -1, which would be 3 times -1 squared minus 4. All right, 3 times the -1 squared, -1 squared is just 1. So it's 3 times 1. 3 minus 4 is -1. So our final answer to this one is the composition is -1. This one required a little more work. We had to first figure out g inverse and then do our composition of these. Okay, let's look at the last one. For the function, find the inverse and the domain and range of the function and its inverse. Determine whether the inverse is a function. Okay, so this is very similar to the first one that we did. So let's look at right now x minus 4 squared. Well, I know that's a parabola that's opening up, and that minus 4 means it's just shifted to the right 4 units. So this is the graph x minus 4 squared. Domain of this one is all real numbers or -infinity to a positive infinity. The range is going to be from 0 all the way to infinity, because I'm never going to have anything below the x-axis. But I could have any x value I want to put in there. If I put in a positive 1 million, I would get an answer. Okay, so now let's look at the inverse. So if I said this is the same thing as y equals x minus 4 squared, do our switch, and I'm going to say x equals y minus 4 squared. I'm going to undo with square roots. That brings in the plus minus. Okay, you're undoing a squaring. You're doing that square root symbol. That's when the plus minus comes in. So plus minus x is now, our plus minus square root of x is now going to be equal to y minus 4. So I would add 4 to both sides. So I have 4 plus or minus square root of x equals y, which is the same as f inverse of x. Okay, so domain and range now of the inverse. I'm just going to do my switch. So my range becomes my new domain, 0 to infinity. My range of the inverse is negative infinity to infinity. And then the last step, determine if the inverse is a function. I know it is not because this original failed the horizontal line test. It hit twice. So this is, so f inverse of x is not a function. So these four types of problems are all to be expected on the test for tomorrow. If you can do these four and you feel comfortable with these four, you're set up well for the test tomorrow. But if you're not sure on any of these, it's going to take some extra time, do some extra review so that you can do these types of problems because this is what's going to be on the test tomorrow. And then the warm-up, we'll do the warm-up real quick just for another practice problem. Says find the domain and range of the original function, find the inverse, determine the inverse is a function, and then find the domain and range. Okay, so square root of x plus 4. So if we thought of this graphically, x plus 4 is actually going to move it 4 units to the left. So I'm going to be here at negative 4, and it's going to look like that. So my domain, my possible x values are from negative 4 to infinity, and then the range is going to be from 0 to infinity. To find the inverse, square root of x plus 4, we're going to make our switch. So x equals square root of y plus 4. And now we will square to undo this. Simply squaring does not bring in plus minus. So we have x squared equals now just y plus 4. So x squared minus 4 equals y inverse, which is the same as f inverse of x. Domain of this inverse function is 0 to infinity. Range is going to be from negative 4 to infinity. And is this a function? I could say yes, this one is a function because the original passed the horizontal line test. So I would say yes, f inverse of x is a function. So that was a pretty quick run through of what we've been doing up to this point. All right, so make sure you're comfortable on working through those problems. I'll post these slides. I'm recording this video, so I'll put the video up as well so you can check to make sure that you can do those for sure. All right, let's go into today. So today is graphing radical functions. Typically, this would be a no calculator concept since we're going to be testing at home. You can use a calculator, but it's probably not going to be one that's necessarily going to help you with a calculator. The problems are going to be more conceptual than actual calculation type problems. Okay, so this idea of graphing, like I said, we're going to be having problems that we need to know a parent function, and then we can graph if there's a shift, if there's a stretch, if there's something going on with it, we can graph what that new function is going to be. This is not an entirely new concept because we've already been doing it to a point. All right, so the idea of this parent function. So the parent function is just a baseline function where we are starting from before we throw all this other stuff into it. So we've talked about this one, square root of x. So square root of x is one that you should know as soon as you look at it, you know that it looks like this little line going from the origin, going out into the first quadrant. Okay, this is where we're going to be starting from. This is our baseline. So then if we start to change it up and say we do like, say we do like y equals square root of x plus 4. Okay, we know that. All that's going to do is shift it to the right, or I'm sorry, shift it to the left 4 units. Well, if I change this up and I say, well, square root of x plus 4 and then minus 3. All right, I know it's going to take this same shape and it's just moving it. If I change this up and I say, well, what about negative square root of x plus 4 minus 3? Okay, this negative represents a reflection over the x-axis. So it's going to take on the same shape. It's just now going to be reflected over the x-axis. So it's now going to be down under the x-axis where the arrow is going. But it all stems from this parent function, understanding that the square root of x is our graph right here. All right, and some key coordinates to recognize. Well, I know on my parent function, I have the coordinate 1, 1. I also have the coordinate 4, 2. Understanding or being able to determine coordinates are going to help you as well, because we're going to make some adjustments to coordinates based on whatever function they give us. If we're to think about domain and range, I know my domain on this is from 0 to infinity, and I know my range is going to be, for the parent function, 0 to infinity as well. It's never, for the parent function, it's never going to go into negative x values or negative y values, but 0, 0 is 1. We are defined here at the origin. We do have that. So today is all about transformations. So transformations of functions can be translations, which translations are the same thing as a shift. So whenever you see the word translation, just think of it as a shift, literally taking that shape off the page, moving it, and putting it right back on the page. But now this stretch and shrink is actually changing the function a little bit, and it's going to be changing our coordinates. And so a transformation is an all-encompassing term saying, all right, it's changing. A translation is just a shift. It doesn't mess with the shape at all. But this a value here is now going to affect our shape. So if we don't have an a value, the shape remains the same. Once they throw in that a value, our shape will change a little bit. Okay, so based off the parent function, if we have some coefficient out front of the radical, that is going to be a stretch or a shrink depending on the value of a. If it's a negative value, it's going to reflect over the x-axis. The h under the radical is going to represent a horizontal translation, that horizontal shift. And we know x minus moves it to the right, x plus moves it to the left. So it's very counterintuitive under that radical symbol when we're talking about the x. And then the k outside of the radical, that's as is. That's that vertical. If it's plus 5, it's going to move up 5. If it's minus 5, it's going to move down 5. So there's no tricks going on with that one, but that is going vertical. Under the radical is left and right, and it's counterintuitive. Plus means left, minus means right. So let's actually do a couple. I want to graph y equals square root of x plus 2. Well, I know my parent function is going to be, if we were just looking at y equals square root of x as the parent function, I know I have the coordinates 0, 0, 1, 1, and I have 4, 2. And so let's just put those points on here. So this is my parent function, y equals square root of x. Now tacking on this plus 2, all I know is that's changing my y values. My y values are now going to be up 2 units. So instead of 0, 0, it's going to be 0, 2. Instead of 1, 1, it's going to be 1, 3. Instead of 4, 2, it's going to be 4, 4. So now I have 0, 2, I have 1, 3, and I have 4, 4. So now this is that new function, square root of x plus 2. Domain and range now of this new function. So my domain remains unchanged. I can still put in any x value that is a positive x. Somebody put in the chat box, should we graph the parent function every time or just draw the translation? Both are good to do, okay, but I'm only going to grade that final translation. That's what I'm going to look at to see if that's in the right spot. But how I'm working through the problem on here is how I would do it on a test or anytime I had a problem. I would draw kind of that parent function, understand what my coordinates are, and then move from there. So domain is from 0 to infinity. My range now has changed because now I'm starting at 2 and going up to infinity. All right, let's look at this one here on the right. So square root of x minus 2. We know that minus 2 actually moves it right 2 units. So moving right, that's affecting the x coordinates. Okay, and so if my parent function was 0, 0, 1, 1, 4, 2, and I'm moving right 2 units, I'm going to add 2 to every x coordinate. So my new coordinates are going to be 2, comma 0, and then 3, comma 1, and then 6, comma 2. Because again, I'm taking these original ones over here of my parent function and simply adding 2 to the x. The y remains unchanged, but the x does change. And so when I go to graph this, I'm going to have over here at 2, 0, and then over here at 3, 1, and then over here at 6, 2 would be somewhere over here. And it looks like that. Domain and range is now from 2 to infinity, and range is from 0 to infinity, and it's 0 inclusive. That's why I said knowing the coordinates of your parent function will help you to be able to move stuff around. Now let's take it up a notch. Let's look at if we have a multiplier going on that's going to affect the size and shape of it. So again, we're still starting with that same parent function, the y equals square root of x. We're still working with that. Now this -2, I know that negative is representing a reflection over the x. And it's also that 2 is creating a vertical stretch. So again, let's just look at coordinates of this original. So the parent function is 0, 0, 1, 1, 4, 2. I'm looking at that multiple of 2, I'm not even worried about the negative yet. I'm just going to work with that multiple of 2. That is going to change. Every output is going to be multiplied by 2. My x is not changed. If I put an x as 2, x is 2. But I'm multiplying by 2, and that's going to change my y. So now 0, 0 is still going to be the same. But now my next coordinate will be 1. That remains unchanged, but the output is a multiple of 2, so that becomes 1, 2. The input on the other coordinate 4 remains unchanged, but it's going to be multiplied by 2 to end up with 4 as my output. All right, so this is not the final graph. I'm just graphing where we're at. This isn't the final answer yet. So we got 0, 0, over 1, up 2, and we got over 4 and up 4. So 1, 2, 3, 4. So we have something that looks like this. This is not our final answer yet, because our final answer now is going to come from that reflection over the x-axis. So if we were to reflect over the x-axis, that's going to change all of our outputs now to negative. So this is still 0, 0, but it becomes 1, comma, negative 2, and it becomes 4, comma, negative 4. So I'm still there, and now this is going to be reflected down there, and then this is going to be, did I go too many? 1, 2, 3, up there, not down there. So it's going to look like this. So this is our final answer. This is negative 2 root x is below the x-axis, and it's that dark purple, dark blue color. Domain and range of this function, it's still 0 to infinity. Range now, though, if I think of my range, I can have anything that's below the x-axis. It's never going to go above the x-axis. Okay? This is going to continue going down, 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 down. And so the furthest it's going to go down is negative infinity, all the way up to 0 inclusive. So this is kind of a little bit different to think about, thinking down, up. So it's negative infinity, it's going all the way down, it's going all the way up to 0. Okay, let's look at this one here on the right. So now we have negative 2 root x plus 1 minus 3. Well, let's start peeling off what we know. We know it's going to be a reflection over the x. We know it's going to be a vertical stretch by 2 by a factor of 2. The x plus 1 means it's going to move left 1. And the minus 2, it's going to, or minus 3, it's going to tell me it's down 3. So we have all this stuff going on. Okay, here's another little trick. Once they start to get more and more advanced, or more and more involved, I guess, this is how I attack them. Okay, so that left 3, or I'm sorry, left 1, down 3. That's the first thing I'm going to tackle. And this left 1, down 3, I'm going to mark that point on my coordinate plane. And I'm going to draw in a new coordinate axis at that point. So I am treating that as my new origin. Okay, so I've taken into account all that shifting that I went left 1, down 3. I've done all that shifting. I have a new coordinate axis. So now all I'm looking at is this same function that we've already worked with, y equals negative 2 root x on my new coordinate axis that I just drew. Okay, Well, I already did all that work from the previous problem. I know that it's going to be 0, 0. I know it's going to be 1, -2, and it's going to be 4, -4 from the origin. In this case, it's from my new origin. So this new origin in red, all I have to do is graph these points. But again, I'm going off of this new origin here, this red dot. And so 0, 0 is going to be a point. So I'm going to put that right at the origin of my new coordinate axis. From this, I'm going to go over 1 and down 2 from that new coordinate axis. And then I'm going to go over 4. So 1, 2, 3, 4, 1, 2, 3, 4. And I'm right there. So this is my new graph. So that shift, that left down, I create a new axis, and then I just go off of coordinates that I already know with my new origin as the origin I'm working from. Okay, so my domain on this one, my possible x values, well, the smallest it can be is -1 because I shifted over 1 all the way to infinity. And then my range is a -infinity because it's going to keep going down, down, down. So I'm thinking I'm coming up all the way to a -3 inclusive. Okay, so think of this new origin. You might have to focus on this, study this idea for a few minutes before it really sinks in. But moving it to this new origin is very helpful because then once you have this new origin, you already have your coordinate points, and these are kind of like modified coordinate points, and you're going off of your new origin for these points. All right, let's do one more parent function, and we'll do a couple examples with this, and then that'll be it. So this is the cube root of x, and we haven't done too much with cube root of x. We've done some stuff with x cubed, but cube root of x now is another one that we should become more and more familiar with. Starting out with some coordinates. Well, I know 0, 0 would be a coordinate. I know 1, 1 would be a coordinate. So if I did y equals the cube root of 1, that equals 1. And I know -1 is also a coordinate. So we need to have that baseline for our parent function, know what coordinates we're working with. Domain and range for a cube root function is -infinity to +infinity, or you could say all real numbers. Anything will work. These arrows here on the end say it's continuing on to the right and to the left. Range is also a -infinity to infinity, or all real numbers, because those arrows are going up and down as well if we think vertically. So cube root is another function that we should become more familiar with, that if I ask you what cube root of x looks like graphically, your mind automatically jumps to, okay, yep, I have an idea. It's kind of this sideways S shape, first quadrant and third quadrant. And in terms of transformations, same rules apply. All right, you might probably don't even necessarily have to write this one down, but it just has cube root, still that A coefficient out front. If A is positive, or if A is negative, it creates a reflection. It's going to create a vertical stretch or shrink. Minus H actually moves it to the right. Plus H moves it to the left, only thinking horizontal. Plus K would move it up. Minus K would move it down. So nothing new with that, but same rules apply for cube root. So let's do a couple transformation problems now using cube roots. So if I had the cube root of x plus 3 minus 1. So the same thing, I'm going to create a new coordinate axis. I know this is going left 3, down 1. So I'm going to go left 3, down 1, and create a new coordinate axis here. And I'm going to work specifically from that new coordinate axis. That's my new origin. I don't care about the origin where the two black lines intersect. I'm only looking where these two red dashed lines intersect. I'm going to go off of that. There is no coefficient on this, so really all I need to worry about now is cube root of x. I've taken care of that shift by creating this new dashed lines for my new axes. Okay, and I know my points are going to be -1 from the parent function, 0, 0, and 1, 1. And I'm going to use those coordinates from my new coordinate axis location. So I'm going to go -1, down 1 right there. 0, 0 is going to be a point, and over 1, up 1 is going to be a point. But I know this takes the shape of kind of this S laid on its side. So there I've graphed cube root of x plus 3 minus 1. Looks just like that. Domain on this one is all real numbers. Range is also all real numbers, because the arrows are going all the way to the left, all the way to the right, but also all the way up and all the way down. Looking at the second one, a negative cube root x minus 1 plus 2. So I know it's going to go right 1, and it's going to go up 2, and that negative is a reflection over the x. So let's create our new coordinate axes based on this shift. So right 1, up 2 is going to put my new origin I'm going to work from is up here in the first quadrant. All right, and again, I know then all I'm working with, well, I know cube root of x is, again, this -1, -1, 0, 0, and 1, 1. But I want it to be y equals a negative cube root of x. So my x inputs do not change. I'm still going to use -1, 0, and 1. But then it's going to be multiplied by -1 for my output. So my new coordinates are going to be -1, +1. Still 0, 0, and 1, -1 for the third. I'm going to graph those points from my new origin. And so if I go left 1, up 1, I'm going to be right here. I have 0, 0 of my new origin, and I'm going to go over 1, down 1 right there. I know it's going to take this S shape, which looks like this, and it looks like that. So it's kind of going the other direction because of the reflection over the X. Now it's up and to the left, down and to the right. But you could see over from this graph, it was up and to the right and then down and to the left. So that's that reflection piece. Domain, still all real numbers. Range, still all real numbers. I can put anything in there. This idea of creating a new coordinate axis will help you a lot on these transformation type problems. understand the parent function, the coordinates of the parent function, create a new coordinate axis with a shift, and then plot your points on that new coordinate axis, and that will be your new graph. Okay, so your assignment, page 418, 7 through 19, the odds, 20, 25, 28. So you're working in your notebooks, do your best without graph paper, okay? Make the little hash marks. They're not going to be crazy graphs that you're going to have from negative 20 to 20 and negative 100 to 100 or something like that. But do it as accurately as you possibly can on your notebook. Find the domain and range of your final answer for every problem. Okay, tell me, just like on these example problems, we gave the new domain and range of our new function, not just our parent function, of the new function. Take a picture of those, submit it via Schoology. Tomorrow, come with questions. We'll do some warm-up, a couple problems for warm-up, and then you'll go into lockdown browser, but I'll stay on Zoom, and then you'll take your test. Thursday we'll come in, we'll do the next section, and then you can start spring break. So I'll stay on Zoom till the end of our class time, 10:09, 10:08. So if you want to pop back in, I'll be here. Otherwise, I'll see you tomorrow.